Okay, boys and girls, more vector calculus A. So this is vector calculus 3. We're going to pretty much end it today. I just as a word of warning, I was looking at the data analytics from the previous two videos, and I noticed that the average viewing time is like 30%. So basically, people get 2 slides in and then stop. So I was thinking I'm going to do the same here myself. Just do 2 slides because that's all you're watching anyway. But because I'm the professional that I am, I probably will continue to the end. All right. But just let you know I'm watching. I can see what you're doing or not doing. All right. So what I want to do here is that I just want to continue on and introduce two more operators that you might see in your engineering studies. And they're called the divergence and the curl. So you've got, and we've done two already. We've done the gradient, which is probably the most important. We've also done the Laplacian, which some of you will see elsewhere. And so therefore there's two more that I want to talk about. The first one is called the divergence. And the divergence operator takes a vector and it converts it into a scalar. So it's the reverse of the gradient. And this is very important. So if I ask you to do this in the exam and you don't give me a scalar, you give me another vector, you get 0. Because the whole point of the divergence is that it takes a vector field and it reduces it to a scalar field. So it combines the three components into a scalar. And the way it does it is as follows. So it takes the first component, the x component, or the component along the I, and it differentiates that with respect to x. It takes the second component, the j component, differentiates that with respect to y. And the third component, the vz component, the component along k, it differentiates that with respect to z. Now there's a reason why it's of this specific form. But we're not going to go into specifically why divergence is defined this way. From your perspective, you just remember this is a definition. This is what you do. Because people have found that this combination of partial derivatives is very convenient and it occurs very often in nature. In particular, divergence of V occurs a lot divergence of V. If V is the velocity of a fluid, then divergence of the velocity equal to 0 ensures that the mass of the fluid is conserved. There's no creation of mass. So it's a fundamental restriction on the fluid flow. But we're not going to go into what the physics of the divergence operator is. We're going to approach it from a purely mathematical perspective. And what I want you to remember is that, again, let me emphasize, it takes a vector, converts it into a scalar. Boom, boom. And how does it do it? It does it in exactly this way. And so it's very, very simple. It's just, that's all you do. So let's look at this. You've got a vector field A here, x squared y squared along I plus y squared z squared along j plus z squared x squared z squared along k. And we want to get the divergence of A first. Let's do that first. And then we'll evaluate at the point 1, 1, minus 1. So guys, what you do is you take the I component, which is x squared y squared. You differentiate that with respect to x, and you get 2xy squared. Come on, it's so easy. You take the y squared z squared, you differentiate that with respect to y, and you get 2yz squared. And the last one then is 2zx squared. And you add them all together. Because that's what you do, that's the recipe. And then when you've done that, you evaluate it at x equal to 1, y equal to 1, and z is equal to minus 1. So I've done that there, right? So that's just pure application of what the divergence of a vector field is. And then you're going to evaluate it at 1, 1, minus 1. And I think you get 2 plus 2 minus 1. Or minus 2, which is just 2. Okay, that's it. Okay, I could teach. I don't know. I feel confident I could teach lots of people this, and not, and I feel kind of embarrassed trying to teach you guys this because you're so mathematically competent. But that's what it is. So don't be put off by this. No, I do appreciate it's new, and so therefore it takes a little bit of getting used to. But why not get used to it? It's this easy. It's a winner. Here's marks. I'm giving you marks. Come on, I want you into the second semester. Come on, let's go. Now, once you've formulated what the divergence is, you can start doing proving some nice divergence theorems. Something like this. If you have a, I'm just going to do this just because I'm just going to do it because I like this stuff. Yeah, this is just, it looks great to me. But you might see this in application somewhere else. The divergence of Fg, where F is a scalar field and G is a vector field, prove that the divergence of that is F divergence of G plus G dot the gradient of F. Okay, suppose I ask you to do this. Now, it's very unlikely I will ask you to do this, because how would you answer it in the exam at the end of the semester? Okay, but you might see this type of result being used elsewhere in your studies, in your engineering courses. So this is what's going on here. And all it is, folks, is a very simple application of the definition. Okay, first off, you notice that Fg is just F times Gx along I plus Gy along J plus Gz along K, and you multiply each of the components then of G by F, and you get what's on the right hand side there. So what you have now here is you've got Fgx along I plus Fgy along J plus Fgz along K. And what I'm going to do then is I'm going to differentiate the Fgx with respect to x and use the product rule. I'm going to differentiate Fgy with respect to y and use the product rule. And I'm going to differentiate Fgz with respect to z and again use the product rule. So by definition, the divergence of Fg is just, as I said, you take each of the components, you differentiate them respectively with respect to x, y, and z. And in this case, because I'm differentiating a product in each case, I must use the product rule. And that's what I did there in the next line. Okay, so that's what I've done. In each case, you have a product, so you're going to get 6 terms there. On the next line, then, what I'm going to do is I'm going to gather all the f terms together. Okay, so there's 3 f terms. There's 3 terms multiplying f, and then you just do that, and then you take the other 3 terms and you put them together. Now, inside the brackets there, the term multiplying the f, delta gx delta x plus delta gy delta y plus delta gz delta z, by definition, that's the divergence of G. And on the right-hand side, on the remaining term, the term outside the brackets, that's not multiplying the f, the gx delta f delta x, gy delta f delta y, and gz delta f delta z, by definition, that's the dot product of G and the gradient of f. Oh, look at that. So you can do it very, very easily. And there's loads of different results that you can prove using this. And they all look as good as this as well. So it's all very satisfying. Everyone's a winner. Okay. Now, again, guys, from an engineering perspective, there's nobody in Intel who's going to ask you to do this. Okay. So, but you might see this type of operation being done elsewhere in your courses. You might be mystified as to what's going on. And all that's going on is a simple application of the definition of what the divergence is. Because that's all this is. All right. Now, because we've got 2 operators now, mainly, okay, we've got the Laplacian as well, which we're going to leave that aside for a moment. We've got the 2 main operators that we looked at are the gradient and the divergence. And remember what the gradient does. It takes a scalar and it converts it into a vector. And you're probably asking yourselves then, well, if the gradient of f is a vector, what happens if I take its divergence then? Yeah, right? Because that's a natural question to ask. Really, it is. Right? The gradient of f is a vector, and the divergence then works in vectors and converts it into a scalar. I wonder what scalar the divergence of the gradient of f is. All right, boys and girls, what you do, basic application of the definitions. The gradient of f is, by definition, what's on the slide there. And then what you do is and if you want to get the divergence of that, you take the I component and differentiate with respect to x, which gets delta squared f delta x squared. You take the j component and differentiate that with respect to y to get delta squared f delta y squared. And finally then, if you take the third component, the k component, differentiate that with respect to z, and you get the second derivative of f with respect to z, and you add them. Okay, exactly as I said there. By definition. So those 2 lines there are by definition. The gradient of f is that by definition, and then the divergence of the gradient of f is by definition that. And that combination there, the delta squared f delta x squared plus delta squared f delta y squared plus delta squared f delta z squared is called the Laplacian of f. Oh, boys and girls, isn't this beautiful? Everything works out in the end. Where else would you get this in life? Okay. So that's a combination of all the 3 operators. Again, guys, you don't memorize this or commit it to memory. What you do commit to your memory are the definitions of the gradient, the divergence, and the Laplacian. Because once you have the definitions, you can just mess around with this like this. Okay? Don't memorize this. This is a complete waste of time. Okay. You could also then ask, though, well, what's the gradient of the divergence of V? And that doesn't work. The divergence of V is a scalar, and then you could get the gradient of that. You could, but it's a horrible mess. And for some reason, that doesn't work. That doesn't give you a nice little neat formula. You can try it, but it's just a mess. It messes all these derivatives floating around the place. So it's interesting that one way you get a nice, very clean result, and the other way you don't. And that's just the way it is. The final operator that you need to commit to your memory is the curl operator. And for those of you who do mechanical engineering, the curl operator should remind you of calculating the moment of a force. And moment in mechanical engineering is extremely important. It really is. The moment of a vector, you remember, is R cross F. It's really important. You're getting the vector product of the position vector and the force to get the moment. It's just so important, and it's just a simple definition. The curl operator is very similar to that. Okay, and it's a little bit more mysterious than the other two. Okay, and also, unlike the other two, it doesn't convert from one to the other. The curl takes a vector field and it outputs another vector field. Okay, so that's the kind of the difference between the curl operator and the other two operators. There's no difference. There's no difference in this case between the output and the input. Vector is transformed into another vector. And how is it done? Well, let's suppose you have a vector v, vx along I plus vy along j plus vz along k. The curl of v, and it's usually called, the notation is just the English word curl, brackets v. Sometimes you get the triangle cross v, and that's very common as well, actually. So either are very common, but the curl of v is given by that definition there, and it looks very, very complicated. But basically, it's a 3x3 determinant. And if you remember Happy Days, or maybe was it Happy Days last year? No, it was kind of beginning of the sad days, wasn't it? I think. But we definitely did this last year. The 3x3 determinant. But the curl of a vector is a 3x3 determinant, and it's a very special 3x3 determinant. Along the first row, you've got I, j, k, the unit vectors. On the second row, you've got delta delta x, delta delta y, delta delta z. Excuse me. And on the third row, you've got the components of v. And you could ask me, well, why is it this form? Because that's the way God made the curl. That's just it. And again, you could say, well, why is it specifically like this? It just so happens that this describes physical quantities in the universe. It's bizarre, and it looks, you would be persuaded that it can't do, but it's true. And in particular, again, there's an example from fluid mechanics, but if you put something in the water, like a frisbee, kind of a disc in the water, the disc turns as it floats along. And the reason why it turns is because the velocity at the middle of the stream is greater than the velocity at the edge of the stream. And that difference in the velocity causes the disc to turn. And the curl of the velocity gives you the turning of that disc. That's just one application. There's loads of other applications of this as well in other physical situations, but that's just the kind of one that comes to mind most immediately, okay? And again, guys, okay, that's fine. You can write it as a 3x3 determinant. And then what you do is, of course, to evaluate a 3x3 determinant is you write down the first element of the first row, which is just I. You cover up the first row and the first column, and then you do the cross multiplication business. So you get delta V3 delta Y minus delta V2 delta Z. Okay? So then you combine the partial derivatives with the components of V in a natural way. Then the second element of the first row is written down, but you must change its sign. So J becomes minus J. You cover up the first row again, and now you cover up the second column, and then it's delta V3 delta X minus delta V1 delta Z. And the last one then is you cover up the first row in your 3x3 determinant, and now you cover up the third column. You're left with the delta delta X, delta delta Y, V1, V2, and when you do the cross multiplication there, you get delta V2 delta X minus delta V1 delta Y. That's it. That's basically it. Now, it's a lot more complicated than the other two, I will admit, and you need to practice this. So you need to get off your arses, and there's a problem set there. I've done I put some of this stuff on a problem set. You need to practice this, and you specifically need to go onto Khan Academy because they have some like nice little problem sets, quizzes, which give you instantaneous feedback on how much progress you're making. Okay, instead of delaying the progress until whenever we talk to each other on Thursday. Yeah, Thursday. So instead of doing that, you go into Khan Academy and do it instantaneously. So why not? Okay. So practice this. Specifically the curl, because it takes a little bit of getting used to, but once you get used to it, then it's a piece of piss. It really is. It's very, very straightforward. You're going to love it. Okay, let's look at an example. So I've got yz along I, 3xz along j, and z along k. So you need, whenever you're doing the curl, you must write down the 3x3 matrix, okay? Or the 3x3 determinant, excuse me. You must write down that determinant because it helps you. It makes sense, all right? So make sure you do this. Do not be tempted not to write down the determinant. So what I did there is ijk is always the same. The second row is always the same. It's delta delta x, delta delta y, delta delta z. And on the third row, that changes depending on the vector you're getting the curl of. In the third row, the first component is the first component of the vector. So you get yz. And then you get 3xz for the second element of the row, the third row. And finally then the k component gives you the last element of that row, which is z. You cover up so you write down I, okay, and then you cover up the first row in the first column. So you're going to get delta z delta y minus delta delta z of 3xz. Okay, so that gives you the I component of the curl. And then minus j, because that's how you calculate determinants. You cover up the first row and the second column, and then it's delta delta x of z minus delta delta z of yz. And finally then plus k, you get cover up the first row, the third column, and what you're left with then is delta delta x of 3xz minus delta delta y of yz. And then you do the partial differentiation. So on the I component, delta z delta y is 0. Okay, because when you differentiate with respect to y, you hold x and z constant. So you're differentiating a constant there, so you're getting 0. Delta delta z of 3xz is just 3x. All right. In the j component, delta z delta x is 0. And delta delta z of yz is y. Because when you differentiate y or z with respect to z, you get 1. And finally then, folks, in the k component, when you're differentiating the first one there, delta delta x of 3xz, you get 3z. And delta delta y of yz, you get z. And that's what you get. And then you do a little bit of tidying up, minus 3x along I, plus y along j, plus 2z along k. Be very careful with the minus signs relating to the j component, because it's minus j. So in this case, it's minus by minus gives you plus, so you get plus yj. Okay? Beautiful. What do you think, babies? I think this is a winner. Just practice this. Okay? It's very important. Go on to Khan Academy and do the practice quizzes there. Now, with the curl, you can start going crazy with these different theorems that you can prove. I'm writing the first one down because I just think it's so beautiful. I just think there's something very elegant about this. You know, look at all this it's just symbolic, beauty there. There's something very persuasive about it, isn't it? The curl of epsi A is epsi times the curl of A plus the gradient of epsi cross A. That's just the vector product there. Okay? Where epsi is a scalar field and A is a vector field. And you can very easily prove that. I'm not going to do it here on the slides, but you can, you're at home, you've got nothing else to do. You've watched every single thing on Netflix, there's nothing left. So why not just have a go at this? Now, again, guys, in terms of your engineering future, this is not essential. Nobody's going to ask you this at an engineering interview. Okay? One thing I will do, I'll do the last one, though, because there's something interesting, something very kind of fundamental going on here in the last one. Remember now that the gradient of f is a vector. And if you get the curl of the gradient of f, whatever f is, you'll always get 0. That's weird, but it's true. Okay. Now remember, if the gradient of f is what's called a conservative vector field, whenever you take the gradient of a scalar, you always get what's called a conservative vector field. And this is telling you then that the curl of a conservative vector field is 0. And it actually works the other way as well, but we're not going to go into that. Let me just prove this for you, folks, because I think this is nice. The curl of the gradient of f is naught. Now, should you remember this? I don't think so. Come on. You might see it in as I say, when you're slogging your way through electromag or fluid mechanics or something, you might see this kind of thing happening. And should you keep committed to your memory, maybe you have other things to worry about. Okay, but it's very easy to prove that it's zero. And let me just show you what's going on. Again, gradient of f, what is it? It's delta f delta x along I, delta f delta y along j, delta f delta z along k. Now, folks, each of those components, the I, j, and k components, the delta f delta x, delta f delta y, and delta f delta z, they're going to go along the last row of my 3x3 determinant for curl, like that. And then what you do again, folks, as we've done so far, is you write down the first component, the first element of the first row, which is I. You cover up the first row, you cover up the first column, and you get delta delta y of delta f delta z, and then minus delta delta z of delta f delta y. And that's what you get. It's exactly the same, and you can do the same on nonsense. Now, folks, you did this with man. When you're differentiating what are called mixed partial derivatives, the order doesn't matter. So, for instance, if you look at the k component there, delta squared f delta x delta y is exactly the same as delta squared f delta y delta x. The order of differentiation doesn't matter. So therefore, the k component is 0. If you look at the j component again, you've got delta squared f delta x delta z, and then delta z delta x. The order doesn't matter. They're identical, so that goes to 0. And similarly, the I component is 0. And so you get naught. And you'll notice here, folks, that the 0 that I get is not the scalar 0, it's the vector 0. Okay, it's 0 along I plus 0 along j plus 0 along k, because the curl is always a vector. And that's it, folks. And I will talk to you again soon.